Okay. And so, yeah, I was about to say is that this is going to be closer to, so I'm going to kind of come into this like assuming that you had some logistic regression knowledge. I'll kind of review it just really quickly just to kind of show what that is. I'll also review a little bit over bias and variance. Um, and that way, know that a lot of the stuff that we're going to talk about isn't specific to those specific to logistic regression. It's just that in the curriculum, it's introduced via logistic regression. And it's kind of like the natural choice because logistic regression is a linear regression, but done for classification. So it's kind of an interesting application, everything like that. So just kind of know that's what we're kind of going into. And we'll talk about actually evaluating these classifications, which again is what, what's it called? Logistic regression actually does. So let me go ahead and share my screen. Oops, that's the wrong button. Okay. And nope, there it is. Okay. All right. So this is something we'll talk about. Like, this is actually, I think this technically comes after our extending linear regression. So from our versions, module 3, section 28, I think. So just kind of know a little bit that this is where it's coming from. And I'm just going to mention it really quickly. Basically, and we've kind of had hints of this, is that there's something called bias and variance. And bias and variance basically have very specific technical meanings when we talk about well, classification or just machine learning in general. And basically what it comes down to the fact is that your bias, and I believe I had a, okay, I thought I had a little picture here, but our bias basically is when our model is does really well, but it's off the bullseye. So I kind of imagine this, and I think the curriculum actually shows a picture of this, which is pretty classic. It's like if you imagine you have a bullseye, right? Or a target with a bullseye. I'll just kind of like this. And I'll draw my guys in blue here. And if your model is biased, it's trying to hit, into this middle. But what happens is that all your points are really clustered around, like it's saying, oh, it's right over here. And they're all really clustered very close together, but they're off from the actual target. Okay. And so when this occurs, basically this occurs when it's like, it thinks that it's overconfident. It's what we call overfitting. It's basically, oh, I think the bullseye's right here. And once it thinks that the bullseye's right there, it's like, all right, I'm going to go ahead and just keep going that one spot. So it's super confident, essentially, to say, oh, this is the bullseye, where truly it really isn't, right? Now, the opposite of this is, we're not opposite, I don't know if opposite is the right word, but kind of like the contrast is variance. And variance is basically when we have like, you can like, it varies, bigger changes from each, like you can imagine like a bullseye, like an arrow. Every time you shoot the arrow, you're going to hit somewhere different on the bullseye. So you can imagine is that our points are like this, like, maybe 1 or 2 hit the bullseye, but like mostly they're just all over the place. Okay. And this is what we call something with high variance versus high bias. And this occurs basically when, like, you can imagine an inexperienced, this is kind of my little metaphor, an inexperienced person is taking like a bow and arrow and they're shooting and they're not very good at controlling their stuff. So they're kind of just like shooting all over the place. They're not doing a great job. And so this is where you would have essentially a model that's just not as good at predicting, like it doesn't have what we call like high enough complexity. Basically, it doesn't know the steps it should take to get a consistent shooting every single time. Versus bias. Bias is kind of like almost like someone who's, a little too cocky, where it's like, oh, I can do it with my eyes closed, and they can shoot it and they're really well mastered. They know how to hold the bow and they can, let go of it every single time. And it shoots every time in the same exact spot or close to the same exact spot, but they're slightly off. So they're super confident not even looking at it, shooting on the target, and they're hitting the target in the same spot, but they're missing the bullseye. So that's kind of like the difference between bias and variance. And so with these two parts, it's like, well, we don't want something with high bias. We don't want something with high variance. But it turns out there's kind of like this trade-off going back and forth. And it turns out you can actually mathematically prove that's related to your mean squared error, which is what we use for linear regression. We can actually show that it's like, oh, this actually is this part. And so basically, if you increase the bias, or it's like, if you try to lower the bias, you'll, by its nature, will increase variance. And if you decrease variance, you'll increase the bias. So it's kind of like, okay, going back and forth. And again, I'll use the terms when variance, meaning underfitting, and then bias, meaning overfitting. So I kind of think of it like bias being overconfident, variance, you're kind of very all over the place, you're underfitting. And basically it just means that you're overfitting is kind of like you're being almost too exact, you're too confident, and underfitting is like, oh, you're not advanced enough to be able to get consistent results. Okay, so going on here, and this is a nice little graph right here that kind of shows usually this this white right here, or you say this is the error in general, and this blue, or this red right here is a total error. So when we try to train different algorithms, train different models, you know, kind of like what we do with regression, but with classification, we'll make newer models. And, you know, we might change the complexity. And so what we'll see is like, as we increase the complexity, or sometimes we'll even like increase just the amount of time it tries to train, what you'll see is that your error, very, very low, like not very complex algorithms will basically get very high errors, right? But then as we get better and better, more advanced algorithms for considering more aspects, you'll get better and better and better and better. Unfortunately though, if you start trying to make it too complex, it will try to factor in all these different aspects and its error will actually start increasing again. And what's really happening here is that the bias underneath that, when it's very low, is very, very high. But the variance is probably very small because it's not really doing very much, okay? So your bias is very, very high on here, and it decreases as we kind of increase this algorithm complexity. And then the opposite happens to the variance, where the variance starts off very low, and we increase, as we increase the algorithm complexity, our variance actually increases higher and higher and higher, okay? Realizing though, this actually probably is backwards. Is that right? I think I might have mixed those two up. Anyway, so so I'll come back to that. Maybe check that in the curriculum. Now I'm really thrown off that. Which one's wrong? One of these is wrong. And I believe this is wrong. Is that right? Because we increase our algorithm complexity, we have a more complicated model, so our bias should get higher and higher and higher, because our bias is the thing that is saying, oh, you are really certain that this is true. So we basically have really complex things like, oh, it's going to get really, really exact. And this is overfitting. We'll kind of see the model sometimes, like if it tries to fit on a line, it'll do like all these weird zigzags and stuff trying to get every single point. And it's because it's overfitting. It's being too confident. It's like, oh, I know exactly how this works. That's where our bias should go. So these should actually be swapped. So good to know. I'm going to not use this anymore. Wow, I wish I caught that before. Okay. See, this is why you should always make your own stuff. Forget you. Where are you from? Sorry. I'm sure this author is fine. I'm pretty sure I got this. See, oh, here's the target that I was talking about. This is actually very similar to the one in the curriculum too. So you can see this is our ideal model. And we can see here on high bias, we have all it clustered together. Oh, see, they messed it up. Yep. This person's, I should have read this article better before I got this image. They're saying this is underfitting. This is not underfitting. This right here is overfitting. And this is underfitting. Okay, cool. Anyway, with that little side note and confusion, that's bias and variance. And we'll talk about that more and more. I won't talk about regularization techniques since should be something we talked about from last time with other parts. So we'll just skip over this part for now.